Hello and welcome again to Physics Land. Today we are on page 57 of your interactive notebook. Please title these notes Elastic Collisions. Now, you guys just finished taking your test on inelastic collisions, which were all about when you had two things come together to become one thing and move off together. Elastic collisions, slightly different thing. So let's go ahead and get started with a definition. In an elastic collision, also called a bouncy collision, things hit other things and then they bounce. Alright, cool thing about elastic collisions, just like in inelastic collisions, momentum is conserved. Which means that the total amount of momentum before the crash has to equal the total amount of momentum after the crash. Which means that the momentum of thing A initially plus the momentum of thing B initially, for however many things there are, must be equal to the momentum of thing A after plus the momentum of thing B after, for however many things there are after the crash. Which means, using our nifty equation, this is the big one, the momentum of thing A before the crash plus the momentum of thing B before the crash must equal the momentum of thing A after the crash plus the momentum of thing B after the crash. Alright, a lot of stuff going on. But you do it exactly the same. Do the problems the same as inelastic. The procedure is exactly the same. You draw a little picture, you figure out your variables, you plug them in, you solve for your unknown. There is a way to make these problems significantly harder that we are not doing. So, you don't need to worry about it. It's just as hard, just as easy as inelastic collisions. Let's slap an example down on this now. Let's see, just so that you are aware, I am currently 5 lines above the middle of the page, just so you don't run out of room prematurely. Alright, in my example, I'm going to have a thing, and it's going this way. Meanwhile, I have a thing that's going this way. They crash, and afterwards, my first thing has bounced back this way. And thing B has bounced back this way. I want to know what that velocity is. So let's talk about what we know. We know that the mass here is 5 kilograms. We know the mass here is 8 kilograms. We know that this is positive 3 meters per second. Notice that positive means to the right. And this one is negative 2 meters per second. Negative means to the left. We know that after the crash, this is going to the left. And it's sped up. Ooh. So what is this guy doing? What is VB final? Alright, well, Let's write our very long equation. MAVA initial plus MBVB initial equals MAVA final plus MBVB final. Whew. Let's plug in numbers. I got 5 times positive 3. All right. I have 8 times negative 2. Okay. I have 5 times negative 4. Okay. And I have 8. Okay. Let's simplify each little piece. 5 times positive 3. You know that one, hopefully. 8 times negative 2. You know that one, hopefully. 5 times negative 4. You know that one, hopefully. All right. We are not done simplifying yet. I still got positive 15 plus negative 16. That gives me, hopefully you could do that one, all right, now it is an algebra problem. Now it is something that you should be able to do. All I did so far is I plugged in numbers, and then simplified each piece, and then simplified each piece. That's all I did. I haven't done any real math yet, just arithmetic. Now we're ready for math. All right, I need to get rid of this negative 20. I need to get rid of this times by 8. You have to start with the 20. So if this is minus 20, I'm going to add 20 to both sides. That gives me positive 19 on this side. VBF. All right, now what? I need to get rid of my 8, so I divide by 8. This gives me VBF equals whatever 19 divided by 8 is, which happens to be positive 2.375 meters per second. In other words, thing 1 is going to the right, heavier thing 2 is going to the left a little bit slower. They collide. Thing A bounces backwards really fast, and thing 2 bounces backwards a little bit faster than it was going. Interesting. But they have shared the total amount of momentum. If you don't believe me, we can do an easy little check. This is negative 1. Okay, what's this? Is that also negative 1? Well, 2.375 times 8 equals 19. So you got negative 20 plus positive 19 equals also negative 1. So I have negative 1 equals negative 1. Oh, good. Momentum was conserved. I am now, let's see, 1, 2, 3 below the middle of the page, in case you're curious. Okay, so now I'm going to give you something that I want you to write down in parentheses and then completely ignore until next unit. Note. In elastic collisions, kinetic energy is also conserved. Alright, and now don't worry about it. I will explain more about this next unit. Suffice to say, for now, in inelastic collisions, this is not true. It is something special for elastic only. But again, don't worry about it. Next. So, let's now talk about the opposite of a collision. An explosion. An explosion we are defining as when one thing becomes many things. Examples. this would be firing a gun. You have a gun and bullet, which is one thing, and then afterwards you have a gun and a bullet. Okay. This would be jumping off your skateboard. Beforehand, there's you and the skateboard as one thing. You are together. Then you jump off the skateboard, and there's you, and there's the skateboard. Okay. Let's see. Something else. This could be an actual outside of physics class explosion. As in, you have a cup of glass that was in the freezer, and then you pour really hot water in it, which causes the glass to shatter. And you get little shards of glass going off in all directions. You had one thing, a glass, and then afterwards you have little things, little shards going off in all directions. In any case, momentum is conserved. Because it's exactly like a collision. Conserved. It's exactly like a collision, but backwards. So, we start off with our total mass, and whatever its initial velocity is, and then it explodes. And each thing has its own momentum. And if you add up all the momentums of all the little pieces, it has to equal the total amount of momentum that you had before. All right, now we're squeezing in one more example problem there at the very, very end, and then we're done. Example. Mr. Saslow is in a boat. There's my boat. There's Mr. Saslow. All right, the mass of the boat is 150 kilograms, and the mass of Mr. Saslow is 68 kilograms. Mr. Saslow is enjoying his day out on the boat, and then decides that just standing around the boat is kind of boring, and so he decides he is going to jump out of the boat. So here's Mr. Saslow jumping off the boat. And here's his boat over here doing something else. Initially, they are at rest. Nothing's happening. Afterwards, Mr. Saslow is jumping off the boat with a velocity of positive 3 meters per second. I want to know, with what velocity does the boat have after the crash? Alright, well, let's mathify this. M total times V initial has to equal MA VAF plus MB VBF, where the total mass is 218 kilograms and the initial velocity is 0. Where the mass of Mr. Saslow is 68 kilograms and his velocity after the explosion is positive 3. And where the mass of the boat is 150, and we are looking for the velocity of the boat after the explosion. Alright, well, let's simplify. That's 0, because anything times 0 is 0. 68 times 3, that is 204. Plus 150 VBF. At this point, it is an algebra problem that you better know how to solve. You get this equals 150 VBF, divide both sides by 150, and you get VBF. The velocity of the boat after the crash is negative 1.37 meters per second, which means to the left, which is what you'd expect. Because if you're standing on something and you jump one way, it gets pushed the other way. Huh. This sounds a lot like Newton's third law. Because it is. Alright, and that's the end. Please now do the worksheet on page 56.